Thank you for the introduction. I'm Germán Ross. I'm representing today the Embodied AI Foundation. And I'm going to be talking about the role of open source simulation in the area of embodied AI, specifically for ground agents. I'm going to be talking a lot about simulation, and I'm going to be talking about the balance between open source and closed source simulation. And some of my views might be a little bit controversial, but I hope you find them interesting. So we live in an amazing time. So it's the era of AI giving rise to embodied systems and autonomous agents. These agents are basically navigating the real world. They are displaying intelligent behavior, and they have to act in a safe way in the physical world, solving complex tasks. The goal of embodied AI is the deployment of such as intelligent agents, and the fact that they can operate safely in the world. There are dozens of companies, if not hundreds, already around the world trying to make embodied AI like a reality in different domains. So from delivery robots to autonomous driving, mining, construction, manufacturing, you name it. However, there are many considerations when building AI solutions. So first, there is the aspect of how embodied AI is safety critical domain, meaning that, well, we are deploying robots in the real world, and they have the problem that they could harm people, they could basically break infrastructure. So it's a very serious business, and we need to put safety at the top of everything, right? It's key that everything that we build in the context of embodied AI can be deployed with the highest level of care. And it's critical that the scrutiny of these systems remains very, very high. I understood this kind of well when I joined Toyota Research back in the day. At first, I just wanted to build fast, put out there new agents that could do amazing things, and didn't care so much about safety at the time until actually someone was about to get hurt. The safety driver was running the latest version of the code and ran into issues. That's where I started to notice, like, okay, this is a serious business. People can actually be hurt, people can die. We need to take safety very, very seriously. Also, embodied AI solutions typically need to deal with a complex and ever-changing world. Like, situations are very diverse, and we need to consider the long tail. So that distribution of very infrequent cases, that even though they are infrequent, your system needs to be able to address in order to be considered safe and to be able to deploy in the real world. Also, there is the need for speed. So we need to put things into production fast. We need to develop, validate fast in order to be compliant with what society requires from us. So it's important that we find ways to accelerate this production cycle. So in order to support all these previous points, we need very powerful and versatile tools. Tools that can amplify our capabilities to make this tremendous challenge a reality. All these tools need to be flexible enough to handle the tsunami of technologies that we need to integrate together in order to realize embodied AI products. One of the key tools that I'm going to be talking about today is the need for simulation. So simulation is one of the key tools that is going to allow us to address many safety concerns, focus on this expedited productization cycle, so faster development, faster deployment, faster validation, and faster reaction to feedback that we gather from the real world. Okay. Simulation tools like the one that you are seeing in the background are becoming pivotal to deliver good embodied AI solutions. And it's not a surprise, as I have mentioned before, they actually have very clear advantages. So they help us put things faster in production. They accelerate the production cycle. So you can use simulation all throughout your production cycle. So you can do it from early prototyping. You can use it for finding the best configuration of your sensor stack. You can come up with new algorithms, new models that you can quickly validate in simulation before you actually even start to do something serious in production. You definitely use simulation for validation and verification. Like, that's something that 100% you should be doing if you are working in Embodied AI, whatever the domain is. You can even use it after your product is out there in the market. Like, you can play back data logs and find out what went wrong and how to keep improving your product. So simulation comes with you all throughout the production journey of Embodied AI. Another thing for which simulation is very useful is to establish what-if scenarios. So it gives you the capacity to really imagine what will happen if your agent have encountered a completely different thing that you haven't seen in the real world, right? So it gives you that flexibility to anticipate all these corner cases and act accordingly. And it's also helpful to support a wide variety of domains, right? So in your simulator, if you need to deploy in a new domain, in a new geographical area, you don't have to wait until you have your operation teams like doing deployment in the area. You can start by enabling your simulation platform to simulate a new area and find out many insights before you even touch the physical world. However, we need to consider a few questions here, because not all simulation platforms are created equal. And it's important to ask ourselves a few questions. Does this simulation platform truly fulfill my needs? Is it tailored to my business needs? Is it going to be something that can help me accelerate my development cycle? Or do I need to tweak it? Do I need to adjust it? And if I need to adjust it, if I need to tailor it, how do I do it? What's the right way to do that? What are the implications of doing that? And, we need to consider the adaptability and extensibility of these simulation platforms. And a very related question is, considering this, should we opt for open source solutions? Should we consider closed source solutions, or something in between? I'm going to be delving a little bit into these topics. And before I start, I think it's worth giving a disclaimer. I'm an open source advocate. I have been an open source advocate since I was like 10 years old. Today, I'm going to be making a few controversial statements here. I'm going to be advocating that closed source solutions also have a place in simulation for Embodied AI. We'll see. Just hear me out. Keep an open mind. So, simulation platforms are a special class of software because they need to be transformed from their base generic form. Like, simulation platforms, simulation tools are not going to work for your business off the shelf. They need to be tailored. They need to be adapted. In a sense, they need to bloom within your organization in order to really release the full potential of those platforms. That makes simulation platforms something a little bit difficult to work with. So you can just work with a vendor and basically expect things just to work for you like from the get-go. So that's why many companies, OEMs, and companies developing embodied AI solutions typically adopt an approach where they try to build their simulation capabilities internally, which really slows down the company because now they have two different missions. One, really bringing like embodied solutions to the real world. Mission 2, well, we need to develop with tooling because otherwise we cannot really bring embodied solutions to the real world. I would like to defend that there is a way to make all of this work by actually leveraging open source solutions as the base platform and glue, and probably in combination with some very specific and very compact and compact the scope closed source solution. So, okay, let's talk a little bit about that. When we compare open source solutions to closed source simulation solutions, we notice a few problems, as happens with many other tools. The first one is the vendor lock-in. Okay, so I think we have all encountered this. So if you are opting into an open source simulation solution, if you want to transition to another vendor, that's okay. You're going to be able to keep all your capabilities. It's no big drama. You can find someone else that does this simulation development for you, or you can do it internally. You can delegate on the community. You have many options. If you opted for a closed source solution, well, you better get along with your provider, right? Because it's definitely not going to be good if you are not in good terms with them. So then we move into the problem of extensibility and adaptability, what I was discussing before. So off-the-shelf open source simulation is not going to be what your business needs. You're going to need to adapt it. You're going to need to make it yours. If you adopted open source, that's great. You're going to be able to do it internally. You're going to be able to delegate it, so no problems. Closed source solution, you really need to convince your vendor to make your new feature request a priority. And if you have a big account, if you're consuming tens or hundreds of millions, if you're giving a lot of business to that provider, sure, you're not going to find problems. You're going to be at the top of the list. But chances are that if you're a small, mid-sized business, your requests are going to land at the bottom of the list, and then you have a problem, right? And this is one of the biggest problems that people mention when dealing with closed source simulation solutions. Similarly, if you need to integrate with other technologies and platforms within your company, same situation. So open source is very reliable, very helpful. You have full control of everything. Closed source solutions, again, need to talk to the vendor. You need to try to make it a priority, and it doesn't always work. So, okay, based on this, you might think that my stance is like closed source simulation doesn't have a place at all. This is not the message I want to deliver today. I believe that in order to be productive, sometimes closed source solution might have a small and very specific place, which is like dealing with very, very specific niche technologies. For example, if you want to simulate the latest Sony camera for sensor simulation, you might not have another choice than actually going to Sony and get a copy of their model in a black box that you can execute. Sony is not going to give you the code of their camera. They're not going to give you the code of the ISP. But you can still connect it to your simulation platform. So my point, the point that I'm defending here is like when the scope is compact enough and small enough, leveraging some closed source solutions might not be a huge problem if you're getting something very valuable in return. As in, hey, I get to simulate the actual model that I need to simulate in order to put my embodied solution in production. Now, where is a bad place to leverage closed source simulation? Everywhere else. Like your base simulation system should be open source. So the platform that establishes the glue of all the other technologies and the middleware layers and basic functionality, that must be open source. Otherwise, you're shooting yourself on the foot. Like, you need something that can be modifiable, extensible, and flexible enough so that you can use it in your business today, tomorrow, on the day after tomorrow. And whenever there is a good open source alternative for some of those exotic technologies, like the Sony camera module, you should probably embrace it. But in the meantime, it's important that your simulation platform gives you the flexibility to connect to any technology that you need in order to put things in production in a safe way. So flexibility and extensibility becomes key. With this in mind, I would like to present a case of study that is very close to my heart. So it's Carla. It's an open source simulation platform for autonomous ground vehicles. Oops. For autonomous ground vehicles. Let me show you what Carla looks like in practice. So Carla is a flexible simulation platform. As I mentioned, it basically covers autonomous agents. That means from your autonomous vehicles to last mile delivery robots, off-road vehicles for defense, for agriculture, etc. Oops, I don't know why this is moving on its own. It's open source. It's powered by Unreal Engine and OpenDrive. I'll talk a little bit now about that. It has a very modular server client design so that we can keep scaling up through different nodes in order to make the most out of the compute capabilities that we have available today. It provides a very easy-to-use API. This is one of the key advantages of Carla, the simple API, and how people can use that API to build new modules on top of Carla. Finally, so extensibility is at the core of Carla, so it has been fully designed with extensibility in mind. And of course, since it's 2024, it's obviously cloud ready, and you can deploy it in your data centers in the cloud at the scale. So if you're wondering what Carla looks like, you can take a look at the video. So this is how the simulation looks like today. And let me take this opportunity to tell you that this afternoon, as part of the workshop in software-defined vehicles, we're going to be introducing what the new release of Carla and what Carla looks like from next week. And it's going to be very different. It's probably going to blow your mind. So if you're interested in this topic, please come and check it out, because we're going to be discussing a bunch of new features that are very, very interesting. And here what you can see is your typical city simulation, highway simulation with traffic, pedestrians, etc. It's fully configurable, so you can get access to all type of sensor information, so cameras, lidars, ultrasonics, etc. All type of ground truth. You can by using the API, you can really do anything with Carla, from data acquisition to modifying the environment, run all kind of experiments, train your AI, and so on and so forth. Let me show you how Carla, how Carla, the open source simulation, puts flexibility and extensibility at its core. So this is the architecture of the Carla platform. This is the Carla modular stack. At the bottom, we have Unreal Engine, and Unreal Engine is not open source, it's source available. And as I mentioned before, sometimes you kind of have to cope with these limitations for the time being until someone else comes by. The thing that we do in order to cope with this limitation is to make sure that that particular component is properly delimited in the system. And we create a clear abstraction from the top layers to this Unreal Engine bottom module. So everything built on top is the Carla platform, and is fully open source, distributed on the MIT license. So first, we can see the Carla server. The Carla server is the core of the platform, and it provides users with sensor simulation capabilities, physics, generation of ground truth, etc. So it basically does most of the heavy lifting. On top of that, we expose the Carla API. And this is an API that people and developers are going to be using to extend Carla. So if you want to create a new module, you will basically do it by calling the Carla API. Typically, we think about it in the following way. We want to bring to the community the key modules and features that are typically needed in this domain, including things like traffic generation, traffic scenarios definition, validation tools, behaviors, etc. And then we want the community to be able to extend all of these capabilities and provide their own solutions. So by using the Carla API, people can, third parties can create their own models that typically are actually better than the ones that we have by default. And we want to get the user the opportunity to basically select whatever works best for them and for their business. So people have the option to use basically all open source solutions or cherry pick what they want to be, closed source or proprietary. Like if there are better APIs for traffic simulation, they're free to choose those better APIs if they need to, etc. So we keep this very open and flexible philosophy in mind. We don't want to put any fences around the simulator. And one of the interesting things is that with this modular pipeline, you can actually distribute all these modules and as clients that run like in different nodes in a full distributed fashion so that you can have very large scalability. Okay, so I would like to talk about some examples of third-party systems and third-party technologies that are integrated with Carla, because as I mentioned before, one of the key concepts in Carla is really to enable this connectivity with any tool that can be useful for you. And in this example, I'm showing Inverted AI traffic engine. I don't know if you're familiar with realistic traffic simulation, but it's very, very hard to do realistic traffic simulation. Traditional approaches end up producing traffic that looks like robotic, right? It doesn't look natural, it doesn't look human-like. Inverted AI created a new traffic module by leveraging thousands of human drive hours. They basically created an API around that model that you can call from anywhere. And it's integrated with Carla. You can use it. So you can use our default module, and you will get reasonable traffic simulation, or you can call Inverted AI and you will get a very compelling human-like traffic simulation. And if you are in the business of validation of autonomous agents in this context, you probably want to get something like this. So the closer you get to the real-world fidelity, the safer it is to draw conclusions from your experiments. Another example is synchrotron solutions. They have developed a suite of products that significantly extend the capabilities of the base platform and make Carla more user-friendly. So they have built amazing web front-ends, vehicle configurators, data acquisition pipelines, all kind of tools. Some of them are open source, and we're very thankful to them for donating some of these to the open source community. And some of them are not open source yet. We hope that over time, more and more of these models will become open source, but we also understand that there is a business model behind this that make the company survive. But this is a good example of how when you keep the doors open, the community comes up with interesting trade-offs between open source and closed source in order to serve developers the best they can. Then we have AVL, and AVL is a renowned simulation company. I don't know if you're familiar with them, but they're super huge. They decided to integrate their simulation solution for off-road simulation of tractors and other agricultural vehicles into Carla. And this is something that would have been unbelievable like 5 years ago. The fact that a large company decided to adopt open source as a distribution channel for their model, even if the model itself is not open source, is huge in this domain of ground vehicles. I don't think this has happened before. So, yep. ANSYS, another giant in the space of simulation, did something similar with their real-time radar simulator. So for context, so radar simulation is one of the hardest problems in sensor simulation. It's very hard to simulate radar, and it's harder to simulate radar in real time. So ANSYS developed this new real-time radar model, and they decided to distribute it through the Carla ecosystem. So if you are in the market looking for amazing radar simulation, you have this as an option. Of course, you can also use our default radar simulator, which is fine. If you want to move to the next tier, you can always, talk to these guys and basically get it done. So a matter of trade-offs, right? Finally, for my last sample, we are ultra connected with the open source ecosystem, being as open source ourselves, right? So this is the example of Sumo. Sumo is a macro scale traffic simulator, so basically driving like large volumes of vehicles, so that you can do all type of analysis, density analysis, blockage analysis. So do you have enough capacity at your intersection? Do you need to change the frequency of your traffic lights in order to support, more traffic, etc. And the community connected it with Carla, so you can benefit from their macroscopic traffic simulation capabilities in combination with what the Carla platform offers, so sensor simulation, being able to connect this to validation services, etc. So again, flexibility to tailor the platform to fulfill your needs. In my opinion, that's really one of the huge advantages of using open source as your core platform. Okay, but the benefits of having an open source and flexible platform don't end here, right? I think one of the greatest virtues of Carla is how it has helped shape and accelerate the progress in ground embodied agent research. The fact is that open source means that it is accessible by many people, right? So the entire research community can use it. Scientists can share results. They can compare results, and they can keep building upon each other's results. And that's a great accelerator for research. Moreover, since the platform is open source, researchers can easily adapt, modify, and extend Carla to fulfill their needs and to be able to run new experiments. In the context of research, Carla has been cited more than 6,000 times, which is huge in the domain of ground vehicles. And it has been used by some of the top scientific publications, demonstrating really the value of the platform to help develop new groundbreaking ideas. But we didn't want to leave it here. We thought that we could do better. We decided to keep helping the research community. To that end, we introduced what we call the Carla Autonomous Driving Challenge as a set of modules built on top of the Carla platform. So the idea of the Carla Autonomous Driving Challenge is to serve as an open testbed to evaluate the driving proficiency of your agent, right? This is in the context of automotive. So we have like a common framework with a set of common maps that everybody has access to, a common database of traffic situations, and a common set of metrics so that we can easily compare the benefits of different ideas and different agents. Again, this has been thought with the main objective of accelerating research in the community. And we did it basically because we thought that the research community needed a challenge, that they needed extra motivation to work on new ideas. This is what the challenge looked like. So basically, agents are asked to drive throughout different routes, throughout tens and hundreds of miles. They're going to be encounter very complex traffic situations that they have to deal with. The idea here is that they should be able to complete the routes and minimizing the number of infractions, right? So we want to come up with very safe agents that are able to do the job, but in a safe way. So we synthesize thousands of traffic situations. So you can kind of like imagine this testing as the worst day in a human driver. So it's a few hours of simulation, but they are going to be packed with very interesting use cases. So we came up with a set of common metrics for evaluation. So in a nutshell, so we wanted to make sure that completing the route had a lot of weight, but not at all costs. So every time you commit an infraction, your score gets deducted. We didn't want to come up with very complex metrics. We wanted something simple that people could understand. And so far, we're not advocating that these are the best metrics, but these metrics have the virtue that are easy and understandable. Also, if you are wondering of what type of situations people are going to face, here there are some examples. So, you need to know how to pull off a parking exit. When there is traffic, you need to be able to yield to emergency vehicles, manage complex cutting situations, obstacles in the middle of the road, and so on and so forth. So this is one example where there is an obstacle in the middle of the road. So you are the black sedan. You need to wait until the adjacent lane is free so that you can maneuver around the obstacle. There are many situations like this during the challenge. The challenge has really motivated the research world to come up with new ideas, new models, and new training methods to keep getting better and better. We just checked the green curve on top. That's the results for the first version of the challenge, what we call the challenge 1.0 that we started back in 2019. When we started the first edition of the challenge, the driving scores, the proficiency driving was very low, just around 8%. But then year over year has been kind of like doubling until people reach very, very high numbers. At some point, we decided that the community was ready for an even bigger challenge, and we transitioned to the second version of the challenge, what we call the Carla Challenge 2.0, which basically increases significantly the complexity in the routes and the amount of traffic situations and their complexity, and that's the curve that you have at the bottom. So we started in 2022. The first year, people got a very low score, but the scores are already doubling each year. So we're seeing a lot of progress in the community. So when you come up with the right, challenge, with the right motivation, the community responds. Oops. And this is this year's winner, Carl Lava from LLM4AD. And something interesting to notice here is that this team is a combination of industry and academia. From industry, we have Wave, which is a famous Embodied company that raised I think $1 billion this year. They are participating in collaboration with the University of Tübingen, which is a very respected AI center in Germany. And they came together with an end-to-end approach that leverages visual language models to do the driving, and it has been very interesting. If you care about this type of approaches, tomorrow at the vehicle software summit, I'm going to be talking about end-to-end approaches on Carla. Let's see this in action. So this is the Carlava agent in action that took the first place in the competition. What you're going to see here is while driving is able to tell you exactly why is it taking the decision that it's taking. It can justify why it makes sense to stop, reduce speed, etc., go around objects. So scoping with one of the key limitations that we thought end-to-end models will never be able to go to production because, well, we couldn't do good explainability of them. But now, thanks to this type of models and the emergence of LLMs, multimodal vision language models, we are able to do introspection of what our models are thinking and why. So we have that additional safety component accessible. Finally, I would like to conclude this talk by highlighting one of the fundamental advantages of open source solutions. You can create strong communities that are engaged and contributing to your project, right? And that's very powerful. So in the case of Carla, our community is formed by automotive and robotics enthusiasts and developers, simulation engineers, students, and if you like this topic, hopefully you will be part of this community soon. We have around 2 million downloads a year, 1,000 daily active users, and around 100 active contributors. We have an amazing ecosystem of integrators and third-party providers, including Synchrotron, ANSYS, AVL, Fortelix, and many others. Again, if you're interested in ground robots and embodied AI simulation, I invite you to be a part of this community. This concludes my talk. I hope that you found it interesting. I hope to see a lot of pushback during the question session. And you have a QR code in case you want to find more about the Carla open source project. Thank you.